3D biped. Okay, so what I'm going to do is I'm going to have a model of a biped, and that model will be something like this. To draw it in some what do you call, non-zero reference configuration might be better to start with. Okay, so there are 3 joints here, 3 joints here, 1 joint here, 1 joint here, and they're all revolute joints. And then we need to describe so these joints are the joints where you have motors, right? You also need to describe the orientation of the robot with respect to the world frame. And there are many options here. You could describe that with respect to this link, this link, this link, whichever you want. Just that makes it easier if you have like a democratic choice, which is basically the one which is middle way, right? So let's just use that to be the torso to be the link which is reference to the world frame. So 3 DOF, right? 3 DOF because three rotational DOFs, 3 translational DOFs, right? Because there are 6 degrees of freedom associated with a rigid body, 3 due to translation, 3 due to rotation. So this is how it looks. How do you actually do this? You put it in the 0 reference configuration, because I'm going to use the 0 reference model. Okay, and when I say left, right, it's going to mean the robot's left and right and not my left and right. And then we assume that the robot is going to walk this way. So I guess I'm going to show a face or something. So the robot is seeing this way. So when the robot is seeing this way, it's basically this part is the left, it's left, and this part is its right. Okay, so let's just abbreviate that by L, abbreviate this part by R. Okay, now let's start indicating the degrees of freedom. So remember here we have 6 for the showing the body with respect to the world, 4 per leg, and 4 here. So it's 6 plus 4 plus 4 equals 14. So that's pretty complex, more complex than we've ever seen anything in this course. Okay, so there are 14 degrees of freedom. So let's just show them here. Now I can make a choice on how I'm going to show the rotations, and the way I choose rotations are in the following way. So for the joint at the hip, there are 3 joints, and those 3 joints are going to give me pitch, roll, and yaw. And the way typically what you do is you put the yaw motor first. So that motor is going to be this way. Then you put the roll motor. So that's going to point in the X direction. And then you put the pitch motor. Okay, now this should all have been, it's overflown. Let me just put it this way and this way. Okay, so it's close to this joint. Okay, so the reason why you do it this way, this fashion, is because the pitch joint, or the pitch joint basically tells you rotation, the swinging motion from back and forth. That's the one which is last, because that, so if you had put this before, so first of all, each joint has its own motor. If you put a heavier motor down, then you need to swing all that weight in front. So for example, if you switch the hip roll with the hip pitch, then what will happen is, as the leg swings forward and back, it will need to provide the energy to move that heavy roll motor, right? And you want to avoid that. You want to keep as little weight which is spun from one place to another. So you want to keep the distal joints to have the least weight. So you basically put the pitch motor at the end. Okay, now once I put these in this fashion, okay, and then there is this one for the knee. I need to choose the angles. Now, the way I choose the angles is I choose this upwards, because if I then curl my fingers along, point my fingers along the axis, and then I curl my fingers, then that means that positive rotation would mean that the leg is going away from it's going on towards its left. It's going to turn left, right? So that's how I'm going to use it. And then for the pitch, uh, I want the positive direction to be this way, such that when I curl my finger again, the positive rotation would mean it's going to do is this, going away from it's going to move in the sagittal plane towards the left. I'm somehow not clear about this abduction, adduction, and I don't want to confuse you by saying that. So that's going to give me motion that way, and that's going to be positive. The pitch is always going to be such that when I turn it in the front, when the leg moves to the front, it's positive, and same for the knee. Okay. So once that is done, I can move to the other leg, and then there's a pitch, and then there's a pitch. Okay, so again, if I want to maintain the same thing, that is, if the leg, for the leg to, when the leg is going away or is turning this way, you get a positive rotation. Then what I need to do here is I need to put this arrow downwards, such that when you curl the fingers, if you move the leg away, it's going to give positive rotation. For the roll, as said, once you turn clockwise here, your leg goes away from the vertical midline. Similarly, if you want to do the same thing here, then you need to move the axis in the opposite direction to the roll axis for the left leg. And then for this, I'm going to keep it the same, because I want positive direction to correspond to hip motion front, and positive direction for the knee is the same. Okay, so this is my joint structure for the two legs. Now I'm still left with the joints for the translation. So in this case, XYZ. And I basically put my XYZ right here. So what I'm going to do is I'm going to show this with a different diagram, because it's going to clutter everything here. So I'll just take this. So now what I need to do is I need to put the 3 translation and 3 rotational degrees of freedom. So first we'll have rotation about X. Okay. Then we have rotation about Y. And really, I don't need to have like separate prismatic joints for that. Just put it in one place. X is going to be this way, Y is to the left, and Z is positive. So I just combined 3 linear joints into one place, which is not a problem. Then I'm going to have rotations about X, Y, and Z. Okay, now I chose them to be 1, 2, 3. Okay, so first is the rotation about X, then rotation about Y, and then rotation about Z. However, in my earlier lecture notes, I stuck to the 3 to 1 convention. So this is a different convention than what we have seen so far. But really, it doesn't really matter. It's not going to change anything, because irrespective of what configuration we use, we're just going to derive all the equations all over again. Okay, so that is the kinematics. Okay, now once you have this kinematics, then you need to find position vectors. Okay, and what I've done is I've used the 0 reference configuration to find the position vectors, which is very straightforward, really, because you know the positions of these joints in the world frame. Okay, like for example, if you think that this, if you so for example, this is 0, 0, 0, then this is going to be along the z-axis. So 0, 0, I think I took it to be L0 divided by 2. And then this is going to be X is 0, Y is, let me not clutter this on the same figure. Let me just draw a new one. Okay, so this one is 0, 0, L0 divided by 2. I believe I took this to be the width W. So this is going to be X is 0, Y is width W, and then the length is along the Z-axis is going to be 0. This one is going to be 0 minus W0. Let me just check this quickly. Yeah, that's right. And then this point is going to be, X is going to be 0 again. Y is going to be along the left, so W. And then the Z is going to be, since it's relative to this point, and I'm assuming this length is L1, it's going to be minus L1 because it's downwards. And this is going to be 0 minus W minus L1. And then I also need the ankles. So it's be 0 W minus, I assume this to be L2, L1 plus L2. And then this point is 0 minus W minus L1 plus L2. So pretty much, you can put this as 0, 0, 0 and do it. You could, and the good thing is that once you put this X, Y, Z in the right way, you will actually get it to move. So it won't be that the base is in the ground level and the feet have penetrated the ground the way it is this way. It'll actually move depending on how you set X, Y, Z. So don't worry about that. Anyway, so the zero reference configuration needs this configuration. It needs me to define the pins, and you can see the pins. For example, the pins, this pin is going to be 0 for the X. It's going to be minus 1 for the Y because this arrow points in the opposite direction as Y, and 0 for the Z. So that's the same as that one. This one is going to be X is 1, Y is 0, Z is 0. This pin is going to be 0, 0, 1. This pin is, since it's pointing in the negative Z direction, 0, 0, minus 1. This is pointing in the negative X direction, minus 1, 0, 0. This is along the minus Y. So, and these pins are just along the axis as they are. So we have the pin use, we have the positions, which are these, and then you also need the positions of the center of mass, which I'm assumed to be midway. So the position vectors is no big deal. You easily have them. The second thing is you need to find the velocity. The velocity is found by using diff of the position or using the Jacobian. Either one will do. So this is the linear velocity, lin. We also need the angular velocity. Okay, and specifically we need that in body frame. And that we need it in body frame because as I've told you earlier, it's easier to describe the inertia in the body frame. So that is a recursive formula which I've discussed in one of the classes. I don't have it here, but it's in my code and you can see it. Basically, it finds the angular speed of the zero joint and then uses that to find angular speed of the next rigid of the next frame and so on. Okay, so that's the position. So that's part one. Part two is to find the Lagrangian. The Lagrangian is L equals T minus V. The kinetic energy is 0.5 summation. Let me check. Yeah, so it's going to be 0.5 m times V dot V across all joints plus 0.5 omega summation omega transpose I omega. So all links. Now, what I did was, in this case, there are actually the body is one rigid body, the legs are two rigid bodies. So I call this the thigh. I call this the calf. Sorry, this is the thigh, calf, right? And then this is the body. So there are 5 rigid bodies. Okay, and I put some mass, and then the velocities will be the velocities of the center of mass, VB. Okay, so that can be found because you know the position vector and you can differentiate. For the inertia, what I did was, this is, by the way, is the body frame. So maybe this notation is not good. I should put omega, which is what I stuck with for body frame angular speed. for the inertia, I have the same thing, which is there's inertia thigh, inertia calf, same thing here, and I body. And I assume that these inertias are actually diagonal, Ix, Iy, Iz. And it's okay to assume that because the inertia in body frame is typically diagonal. Okay. In fact, if you use the off diagonal elements, which you will see if you look at the kinematics or the dynamic descriptions of robots, you'll see that these are typically not diagonal matrices. They are typically fully populated, but you can easily add it. It just means that the equations are going to be a little bit more complex, but it's very easy to extend that. Okay, so once you do that, you find the angular speed, you have this, and so you have the kinetic energy. The potential energy is mass times gravity times the position of the COM. And again, the position of the COM, let me call that R, is, for example, here's RB. And that is, again, something we've already found from the kinematics. So we know this. In the final step, which is the step which gives you the equations of motion, we basically use this equation, dl dq dot d dt minus dl dq equals qj, which is basically the external forces, including torques. And then I also need to impose the fact that this is a floating base object, right? It has x, y, z, and then x, y, z is floating in the air. I need to constrain this leg, for example, to be on the ground if it's in single stance, or I need to constrain the other leg on the ground if it's on the ground. So I need to take the Jacobian of the foot or the ankle, whatever you like to call it, take the transpose times the force, which is now going to be force in the x, in the y, and the z direction, which are, by the way, unknown. So there are reaction forces there which keep this foot grounded or attached to the ground. So since there's a constraint that the foot is grounded, I also need to impose the condition that, so it's called that capital X foot, where X foot is XF, YF, ZF, corresponding to 3 coordinates. Since those positions are fixed, I need to ensure that the Jacobian of XF is constant, right? So then I can take the time derivative of this. Equals, this can also be written as the Jacobian or dx dq q dot, right, equals 0. So that is basically j q dot equals 0. So now I have the j, which is, by the way, Jacobian of the foot. Q dot is 0, but in order to make it the same as, actually, you know what? Let me call this. I need a new name for this. Let's see, what did I use? Oh, yeah, I use q. So q, and I'll define what q is. Q dot is 0, and so jq dot is 0. But then I need to make it. I need to make it at the level of acceleration, so I need to take the derivative again. So jq double dot plus j dot q dot is 0, and then I can write this as jq double dot equals minus j dot q dot. Okay, so I'm almost ready. So this is A, this is B. Let me pull that all together. So from A, I can write mass times q double dot plus c q dot plus g equals, so there is this torque, and I'm going to write it as qj for now. plus J transpose P. Okay, so that's my equation after I take the derivative and so on. This Q, so this, let's try to understand what this Q and this small q is. So Q is, small q is X, Y, Z, phi, theta, psi, and then I used these following notations for the roll pitch yaw of the left leg. So phi L for the left leg, H for the hip, theta LH, psi LH, and then there is another theta at the knee. So I'll call it left knee. Okay, so these are the 4 joints corresponding to the left leg. And then for the right leg, it's simply RH, theta RH, psi RH, and then this one is theta RK. So this is now 6 plus 4 plus 4, that's 14. So that's 14 comma 1. Okay, so now I got Q. This P is 3 comma 1. And then J should be something times 3. So it's going to be J transpose would be 14 times 3, right? Okay, so that's what it looks like. The Q here is the external torques. Okay, now the place where the torques are applied is only these joints, this joint, this joint, this joint, this joint. Okay, it's only those 6 joints where there is a torque, and then there's 8 joints where there's a torque, and the other 6 are uncontrolled. So you could write it as 0, 0. So you could write it as zeros, 1 comma 6 comma 1, and then torque 1, torque 2, so on till torque 8. Okay, the way I write it is slightly different. I write it as this. Okay, B times U, where I'll show what B is. Okay, so B is basically a torque selection matrix. And the reason I do this is because I always want my U, or rather torque, to always be 8 comma 1. Okay, I always want it to be 8 comma 1, no matter what. So if there are 15 controlled, I put 15 by 1. So I just want it to be equal to the number of torque. I don't want to put 6 comma 1. So the way this is done is I find a B matrix, and this can be found by inspection, so that B times T gives me this result, right? It gives me zeros, T1, T2, 3, T8. And the way this is done is, and you see in the code, you can just inspect this and find what B is. It's going to be, see, 1, 2, 3, 4, 5, 6. So it'll be it'll be there'll be 6 zeros, and this things zeros will keep going for 6 rows. Same thing all the way, and then you'll see that it becomes 1 0 0 0 4 5 0 1 0 0 0 0. And this should be 1 2 3 4 5 6 7 8. Keeps going for the first 6 rows, right? Because then the first 6 columns are 0 here. So first 6 rows in my eventual matrix is 0, and then it'll be 0 0 1 0 0 0 0 0 1 0 0. And that keeps happening till I end up with 1 eventually. So it'll be 8 rows like this. So that's my B. Okay, and then as I said, it's only to make it very. If you do it this way, then you can derive equations for any number of links, and it just remains consistent. And it's easy to derive equations. Okay, so this is my equation. I will rewrite this now. Let's call that C. So from C, we have mq double dot plus cq dot plus g equals b times torque plus j transpose p. So that's from C. And from B, if you remember, we can write j q dot double dot equals minus j dot q dot. So now we can combine this to get m minus j transpose j0 qp equals bt minus g minus c j dot q dot. Okay, so this thing here is pretty long, pretty big. This is, remember that this is 14 equations and these are 3 equations. So we're looking at a 17 by 1 system, 17 by 1, and this is 17 comma 17. Now in my code, M will be capital A, that's what I used, and CG, the product, the difference is going to be B. Okay, that's how I wrote it down. Okay, so that is the single stance. For the foot strike, you know, that's kind of simple. You just have to take the integral of this and take the limit as time goes to 0, and what will come out is m q dot m, trying to recollect this, m, right, so m q double dot plus c plus j equals b torque plus j. So now the thing about this is that there are 2 legs. There's one leg which is the stance leg, and the other leg which is the, so let's call this stance and the swing leg. Okay, when the foot strike happens, the stance leg is the one which is behind, the swing leg is the one which is going to hit the ground. And so what I need to do is, there could be and the case I considered is there is a impulsive push up on the trailing leg, the stance leg, and I need to include that in the equations. So it's going to be bt plus j times the j for the stance leg transpose times impulse on the stance leg plus j transpose swing leg impulse from the swing leg. And then I need to take the limit as this goes, well, this is dt, right? And so when I do that, these forces basically becomes close to 0, because when you have an impulse, the gravity and Coriolis force and the torque don't really show up. And so you're left with only, when you take the integral of p dt, you get a force. So let's call this as an impulse, I, and when you take the integral, you get a force. So we have mq dot equals j stance torque p stance, which is now the impulse, plus JSW trans P swing. Okay, looks good to me. And then there is this constraint that now, since this foot is going to be the new swing leg, sorry, the new stance leg, there's a constraint that this point is attached to the ground, and that can be enforced by saying that J swing Q dot equals 0. This is just saying that the velocity of the swing leg, which is JSW Q dot, is 0. That's all it's saying. And so with these equations, what we need to do now is, again, collect terms. So the PST is given to us because that's an impulse the system decides to apply, but SW, the impulse of the swing leg, we don't know about it. So that has to be solved for. So M minus J swing transpose J swing 0 Q dot P swing equals JST transpose PST 0. Okay, let me just quickly check this. Yeah, that looks right. Okay, I think I'm forgetting one thing though. My bad. So when you integrate this equation, you end up with mq dot positive minus q dot negative. So you need to basically put that in here. Mass times q dot. So this is after impulse, right? This is minus, because the integral of q double dot will give you the velocity. And then you need to do the upper and lower limits. This should be q dot positive because the velocity after impulse is only 0. Okay, so that's something I forgot. And then that's be a minus, and that's about it. So that's the equation for the foot strike. So given this, the impulse could be 0 in some cases. Now, given the mass, you can find the speed after impulse and the swing. Okay, so that's basically the equations. So the equations for single stance, which I will highlight here. And then this one. Okay, the final thing before I show you the simulation is I need to derive a controller, right? So the controller is based on control partitioning, or if you like, partial feedback linearization. So what we do here is we use this equation. Plus J transpose P, right? And then we have J Q double dot equals 0, sorry, minus J dot Q dot. Okay, so far we've not really seen this case where we develop a feedback controller for the case where there's a force. Maybe we've done this in the closed chain. So the closed chain, I did have a force in the equations, and I had to get rid of that force because that force is really not contributing. Well, it's basically a constraint force which in a different coordinate system will go away. So in this case, the force is there because I chose the position to describe the floating base at the hip. If I chosen that point to be the foot location, then that force would have gone away, right? Because that point is basically stationary. So how do I actually eliminate these what do you call forces and get me in this reduced coordinate? So here's what I would do. I would write this in the same format as the equations first. Okay, once you wrote the equations, then we'll figure out what are the control degrees of freedom. So as I said, we have 17 things here, right? 17 equations really, but we can only control only 8 of them. Okay, any 8 of them can be controlled. It's your call which. And so what I decided to do is I control the absolute theta, phi, and psi, and that's only because I want to control the torso orientation, and then I need another 5 more which I can control. So I always control the knee joints. Okay, these are fixed. They always control them. Then I have 3 more to choose, and what I did was, if the left leg is on the ground, then I choose the right leg to be the controlled one. So I choose right hip, right hip, psi, right hip. So left is stance. If the right is stance, I choose left hip, left phi, left hip, psi, left hip. This is for the right stance. Okay, so once I have done that, so once I've made a choice on which are the 8 control parameters, then what I need to do is do the following. Okay, so I describe these 8 numbers as my reduced coordinates. So these are the 8 controlled DOFs. Okay, these are either 1, 2, 3, 4, 5 with these three if the left is stance, or they are those first 5 with these three when if it is the right is the stance. Then I can find a matrix just by inspection such that QC is QS times QP. Okay, this is basically the selection matrix found by inspection. So it's found exactly like the B matrix, where you can inspect it and say that these are the elements which need to be 0, these need to be 1, so that QC is gives you those coordinates, those 8 degrees of freedom buried inside Q. So once you identify these, this is like the key step. After this, it's fairly straightforward what you do. So you've done that. Now what we do is this. So QC is, let me write this as X times capital X, where X is Q double dot and P. And then I have M, let me call that a new matrix, A, call it A tilde. So I'm just looking at this equation now. This equation and this equation, I'll call that A tilde X equals B tilde. Okay, and then I'll write the B such that it's B plus BT. 1 second, let me check this quickly. Okay, I think this is fine. Yeah, so what I did, I believe, is that this B and this B is not the same. I need to add a few more columns so that it is actually consistent with this. But it's easy to modify it such that it is B tilde plus BT. Okay, let me see this now. AX equals B tilde plus BT. Okay, so now I can write X as A tilde inverse B plus tilde BT. QC is S times X equals S times A tilde inverse B tilde plus BT. And then S, so then I can take the second derivative is X double dot, since S is constant, right? So there's no S dot, it's going to be 0, equals, why did I do this? So I write QC SX, then I take the derivative, and now is when I replace, this is my bad, this should be, okay, I have an issue here because of this P. I just cannot quite take the, I just cannot just take the derivative. Okay, I'm missing something, which I think I messed up my notation somewhere. Hold on. Well, just a, this is a confusing element. Let me just rewrite this. It's all correct, just that I have my notation all messed up. So so I wrote down AX equals B tilde plus BT. That's correct. Where X is Q double dot P. Okay. Now I also defined QC to be some selection matrix times QP. Sorry, QP. So this is actually incorrect. It's actually Q double dot equals S times Q double dot P, because even in this case, the selection matrix is going to be a constant matrix because it just takes the corresponding rows and puts in QC. So this can be written as S times X, and now it's all consistent. So now Q double dot C equals S times X, but X is A inverse B tilde plus BT. And then by partial feedback linearization, what we need to do is set this to V, where V is QC ref plus KP QC ref minus QC plus KD QC dot ref minus QC dot. So I just use V here. So once we have QC double dot equals V, now we can find what that torque is going to be, because that's what goes to the motors. So S A inverse B, S A tilde inverse P plus PT equals V. And then what we need to do is expand this out. So then we can move this to the left. So we have S tilde inverse BT equals B minus S A inverse B. And then T is S tilde inverse B inverse V minus S tilde inverse B. And this V is right here. Okay, so that is the torque which goes into the motor, which basically gives me feedback, partial feedback linearization. Okay, I'm going to share with you this folder called humanoid, and it has all the things you need to simulate this. So first of all, I'm going to open Derive. Okay, so what does Derive have? Well, it basically derives the equations. So there are 14 degrees of freedom. All the transformations from zero reference configuration, the same thing I did for the pendulum and the passive walkway, except that now I have it in the 3 dimensions, and it's a bit more complicated, but I do the left-hand side. The positions of this is basically positions of the joints. These are all the positions of center of mass. Then I find the velocities. So before that, I find the rotation matrices to get the angular speed in body frame, the omegas, and then the impulse. This is the velocity by taking the Jacobian. Then I find the total energy, which is the kinetic energy, which consists of linear and angular energy. And then I have the potential energy, L equals T minus V, derive the equations, get the A matrix and wrote it as M matrix that's written as A underscore SS, BSS for the right-hand side. Then I get the Jacobian dot. And then this is where I actually generate the equation. So I did not even try, in this case, to get the equations in MATLAB. I just got them straight to C. So this file generates the mex.m file. It writes the B, the tau controller. What else? It writes the equations, and then I also generate the equations of motion, the same file I showed you for the N-link pendulum. Okay. It basically mixes it. But this is the file which is produced. This is the gateway file. Let me run this because it will take a while for it to compile. So while that's compiling, this is delete this. It actually generates a bunch of other files which I have not talked about. It also generates the positions of the left and right foot, I think, velocities and so on. So you will see that it generates a single stance. I should delete it before it generates. So let me just delete this. Okay, so I deleted the single stance file and the EOM file. So that's because it regenerated. Okay, so that's the gateway file. The gateway file is exactly, well, it's very similar to the file I showed you, which does the end-link pendulum. It basically has a few more things going on there because it has to return not only the mass matrix in CNG, it also has to return the Jacobian. So it returns the Jacobian dot from the initial state and the state which is passed and the parameters. So all that heavy calculations is sent to this file called get dynamics, which is now the file which is going to be generated by this MEX file, which is the EOM file. So you see it's generated a single stance file just now. It's actually started to generate the EOM file. It's only 2 kilobyte long for now. It's probably writing it down. You can see it making progress here. It's done. So it's all done. It's mixing now. And the other file which you want to run is the main file. So it makes successfully. So you should see the Meki file. Okay, so now I took some parameters, length, masses, gravity, and then this goes in steps. So first thing I do is I initialize the state. I'm actually solving for a walking solution, so a periodic solution. So I'm using a root finder. Once I find the root finder, I find the Jacobian of the map. And once I find the Jacobian, I do some forward simulation for 4 steps. So let me run this. It will also take some time because this is, it takes about 1 second for animation for computation simulation. So then that affects the how fast the fsolve can solve the problem. So this is fsolve working on getting the solution. So we are in this part of the code. Now it's computing the Jacobian of the map and the eigenvalues. And this is a simulation of the robot. So what I did was just to show you that, and these are some other plots, but just to show you the start and end state are the same, I just put them here. This is showing that the solution is periodic. These are the eigenvalues. You can see that the almost all eigenvalues, except for the first 4, I think, are 0. So the first 4 are non-zero. They're close to 1, which means that beyond 1, if they're greater than 1, the system is unstable. In this case, saying that the system is stable. And this is the fixed point. So I basically took this fixed point, I put it here. If this computation takes a while, so what you can do is, if you want to visualize it, you just comment this whole thing out, uncomment it, and then comment this. And of course, there's a better way to do this than comment uncomment. So let's just comment that, and then you can run this. That'll be much faster because I just use the saved solution. And then we can see it in a different view. If you want to change the view, you go all the way down, change the view. So this is going to be, I think this is side view. Okay, so the gate is not really energetically cheap, because what I'm doing here is I'm just making it sort of stop midway in the cycles. By stop, I mean the swing leg stops, not the overall dynamics doesn't stop. And you can see that the forces, I used a mass of 70 kg, so that's like approximately the mass of a human. The reaction forces are about 1,000, which means that it's about 100 kgs, which is, so 70 kg is the body mass, but then it's 15 kgs in the legs. So the total mass is 100 kilograms. It's quite a heavy person. Then we have left legs, right angles. I was just trying to see the torques, if I can find it. Yeah, the torques. So the torques in the joints, the green one, you can barely see, it's the hip torques, and those are the ones which are maximum of 400 Newton meters, which is actually quite high. It shouldn't be that high. So we can reduce that by not making the leg sort of come to stop in mid swing. We want it to just swing by, and that is not a big issue here. You can actually change it by changing the way you define the reference trajectory. In my case, the reference trajectory was such that I made it stop midway in the cycle, but you don't have to make it stop. So we don't stop our leg from swinging midway in the cycle and then go on. Okay. So this file is, I'll post this file and you feel free to play with it. It actually only solves for a periodic gate. If you want to take this and actually do it on hardware, there are many more steps. Like, for example, you can't just make a robot walk at 1 meters per second or 0.5 meters per second. So the way to do it is probably to make it stand, to make it walk in place, and then probably go to walking. So there is a lot of more steps needed for the robot, like this complexity to go from not working to working. So you need to go through the steps, and I think that's something you can start exploring with the simulation. Once you have the simulation, you can then try making it stand and then walk. And what I would do it is I was do it straight through the finite state machine.